Every telescope ever built, no matter how advanced, is fundamentally limited by the same problem. It isn't a problem of lens quality or mirror size or how far into space we can physically send an instrument. It's a problem of time. Light takes time to travel, and the universe has only existed for a finite amount of it, roughly 13.8 billion years. That means there is a hard boundary to what any telescope, now or in the future, will ever be able to detect, regardless of how the technology improves. Astronomers call this boundary the observable universe, and the name is often misunderstood. It doesn't mark the edge of the universe itself. Almost certainly, it doesn't. It marks the edge of what light has had time to travel to us since the beginning. Beyond that boundary, there could be more of the same, more galaxies, more stars, extending outward for a distance we simply have no way of measuring. Or there could be something else, something current physics doesn't yet have the tools to describe. Tonight we are going to sit with that boundary for a while, and with the strange, unresolved questions that lie past it. Not to solve them, since no one currently can, but to sit with the scale of what we don't know carefully and without rushing toward any tidy conclusion. The size of the observable universe itself takes some unpacking, because the math involved is stranger than it first appears. Light from the most distant galaxies we can detect left its source about 13.4 billion years ago. You might expect, then, that the edge of the observable universe is 13.4 billion light-years away. But the universe has been expanding this entire time, stretching the space between us and that ancient light as it traveled. By the time that light reaches our telescopes, the source that originally emitted it is now much farther away than the distance the light itself traveled. Accounting for this ongoing expansion, astronomers calculate the actual edge of the observable universe to be about 46 billion light-years away in every direction. 46 billion light-years in every direction, centered on us, or more precisely, centered on whatever position any observer happens to occupy anywhere in the universe. This is worth sitting with for a moment. Every location in the universe has its own observable universe, its own 46 billion light-year bubble, overlapping partially with ours, but never quite identical to it. There is no single, universal observable universe. There are as many as there are points from which to observe. Within this bubble, current estimates suggest there are somewhere between 100 billion and 2 trillion galaxies, each containing, on average, hundreds of billions of stars. The number of stars within the observable universe is difficult to even meaningfully compare to anything in ordinary experience. It exceeds, by a significant margin, the number of grains of sand on every beach and desert on Earth combined. And all of that, every star, every galaxy, everything measured and catalogued by every telescope ever built, exists within a boundary that isn't actually the edge of anything physical. It's simply the edge of what we are currently capable of seeing. So what lies beyond it? The honest answer is that we don't know, and we may never know with certainty because of a fundamental limitation baked into the physics of light and distance. But there are several serious scientific frameworks for thinking about what might exist past the edge of what we can observe, and it's worth walking through them carefully. The simplest possibility, and the one most cosmologists consider likely as a baseline assumption, is that the universe beyond our observable bubble looks roughly the same as what we can see. More galaxies, more stars, following the same physical laws, extending outward for a distance far beyond 46 billion light-years, possibly even infinitely. This assumption, sometimes called the cosmological principle, holds that the universe is broadly uniform on a large enough scale, without any special center or edge. Under this view, there's nothing particularly strange happening beyond our observable boundary. It's simply more of the same universe, continuing on past the point where light has had time to reach us. If this is correct, and there's no reason based on current physics to think it isn't, then the observable universe is a bit like standing in the middle of an ocean, with visibility limited to the horizon in every direction. The ocean doesn't end at your horizon. It simply continues beyond what your eyes can currently register, given the curvature of the Earth and the limits of human sight. The observable universe may work similarly, just on a cosmic scale, with light itself, rather than eyesight, setting the limit of what we can currently register. But there's a more unsettling possibility worth considering as well, one that emerges from a widely accepted theory called cosmic inflation. Inflation theory proposes that in the first fraction of a second after the Big Bang, the universe underwent an incomprehensibly rapid period of expansion, growing by a factor of at least a trillion times in less time than it takes light to cross a single proton. This isn't a fringe idea. It's a well-supported component of modern cosmology, developed to explain several otherwise puzzling features of the universe we observe today, including its remarkable uniformity across vast distances. One consequence of inflation theory, taken seriously by many physicists, is that this rapid expansion likely didn't happen uniformly everywhere all at once, then simply stop. Instead, inflation may have ended at different times in different regions, creating what's sometimes called a multiverse, not in the sense of alternate realities from science fiction, but in the more literal sense of numerous separate regions of space, each having undergone its own version of inflation, each potentially developing entirely separate physical properties, separated from us and from each other by distances so vast that light will never travel between them, not in the remaining lifespan of any conceivable universe. Under this model, what lies beyond our observable universe might not simply be more galaxies similar to our own. It might be regions of space governed by entirely different physical constants, different amounts of dark energy, potentially even different numbers of dimensions, each bubble universe cut off from every other by the same fundamental limitation of light and distance that separates us from the edge of what we can currently observe. This is admittedly speculative, sitting closer to the edges of testable physics than the core, well-established elements of cosmology, but it emerges from mathematics that most cosmologists take seriously, rather than pure speculation invented for entertainment. It represents one of the genuine, actively debated frontiers of modern physics, a place where our best current theories point toward possibilities we currently have no way of directly testing or observing. There's a related concept worth sitting with quietly for a moment, sometimes called the cosmic horizon problem, though the details get technical quickly, so we'll keep this part simple. Because the universe is expanding, and because that expansion appears to be accelerating due to a poorly understood force called dark energy, there are galaxies that we can currently see, whose light we can currently detect, that are nonetheless moving away from us fast enough that their light will eventually stop reaching us altogether. In other words, right now, tonight, telescopes can detect galaxies that, given enough time, perhaps tens of billions of years from now, will effectively disappear from view, not because they cease to exist, but because the space between us and them will have stretched so much that their light can no longer outrun the expansion happening in between. Distant future observers, evolving on some far future version of Earth, or perhaps some entirely different world altogether, will look up at a night sky containing dramatically fewer visible galaxies than we can see tonight, simply because the universe will have expanded enough in the intervening billions of years to carry those galaxies beyond the boundary of what light can still cross. This means the observable universe isn't just limited in space. It's also changing over time, in ways that mean future observers will have access to less of the universe's history than we currently do, not more. In a strange sense, we may be living during a relatively privileged moment for observing the cosmos, before an increasing portion of it becomes permanently, physically unreachable to any future instrument, no matter how advanced. It's worth pausing on the strangeness of that fact, without needing to resolve it into anything comforting or alarming. It simply is what current physics suggests, one of many features of the universe that resist easy emotional categorization. Before we go further, it's worth pausing on a related mystery, one that doesn't concern what lies beyond the observable universe so much as what fills the observable universe itself, largely unseen. Roughly 85% of all the matter in the universe isn't made of atoms at all, at least not the kind of atoms that make up stars, planets, or the body you're resting in right now. It's something else entirely, something astronomers call dark matter, detected only indirectly through its gravitational influence on the galaxies and galaxy clusters we can actually observe. We know dark matter exists because galaxies rotate in ways that don't make sense if they only contain the visible matter we can detect through telescopes. Stars at the outer edges of galaxies move far too quickly to remain gravitationally bound, based purely on the gravity of the visible stars and gas we can measure. Something else, some additional source of mass, must be holding these galaxies together, exerting gravitational pull without emitting or reflecting any light of its own. We've measured its effects with considerable precision. We still don't know with any certainty what it actually is. Alongside dark matter sits an even stranger component called dark energy, believed to make up roughly 70% of the total energy content of the universe. Unlike dark matter, which pulls things together through gravity, dark energy appears to be pushing the universe apart, accelerating its expansion in a way that took cosmologists by surprise when it was first measured in the late 1990s. Prior to that discovery, most physicists assumed the universe's expansion, driven by the momentum of the Big Bang, would gradually slow down over time, the way a ball thrown into the air gradually slows as gravity pulls it back down. Instead, precise measurements of distant supernova revealed the opposite. The expansion of the universe is speeding up, not slowing down, and dark energy is the name given to whatever is causing that acceleration. Taken together, dark matter and dark energy mean that the ordinary matter we are familiar with, the atoms making up stars, planets, and every living thing we know of, accounts for only about 5% of the total content of the universe. The remaining 95% remains, in a very real sense, a mystery measured through its effects, but not yet directly understood. It's a strange thing to sit with. Everything we've ever seen through a telescope, every star, every galaxy, every glowing nebula captured in every photograph ever taken of the night sky, represents only a small fraction of what's actually out there. There's another possibility worth considering, quieter and stranger still, concerning the actual shape of the universe as a whole, rather than simply its size. Most measurements to date suggest the universe is very close to flat, in the geometric sense, meaning that parallel lines, extended far enough, would remain parallel indefinitely, similar to how geometry works on a flat sheet of paper, rather than curving back on itself the way geometry works on the surface of a sphere. But our measurements of this flatness, while impressively precise, still carry some margin of uncertainty. It remains possible, based on current data, that the universe is very slightly curved, either positively, like the surface of an enormous sphere, or negatively, like an endless saddle shape stretching in every direction. If the universe is curved in either of these ways, but only very slightly, it would still appear flat within the relatively small region we are capable of observing, the same way the surface of the Earth appears flat when you're standing in an open field, despite the planet as a whole being curved. If the universe does turn out to be positively curved, even very slightly, there's a genuinely strange implication worth sitting with. A universe with positive curvature would, in theory, eventually curve back on itself, meaning that if you traveled far enough in a single direction, you would eventually return to your starting point, not because you turned around, but because the space itself loops back, the way traveling far enough east on Earth's surface eventually brings you back west of where you started. Current measurements don't support this being the case for our universe, at least not to any degree we could currently confirm. But it remains a live possibility, permitted by the data we have, that space itself might loop back on itself, if only the curvature was slightly different than our best current measurements suggest. There's one more idea worth sitting with, stranger than any we've discussed so far, and taken seriously by a surprising number of theoretical physicists, even though it remains almost entirely unconfirmed. It's called the holographic principle, and it proposes something genuinely difficult to picture. The idea suggests that all the information describing everything happening within a given region of space, every particle, every interaction, everything that has ever occurred within some three-dimensional volume, could, in principle, be fully described by information encoded on the two-dimensional surface enclosing that volume, similar to how a hologram encodes a three-dimensional image on a flat, two-dimensional surface. If this principle applies to the universe as a whole, it would suggest that the three-dimensional reality we experience, the depth and volume we take entirely for granted, might be, in some deep mathematical sense, a projection of information stored on some distant boundary surface, the way a hologram creates the illusion of depth from a flat piece of film. This isn't a claim that reality is somehow fake, or that nothing truly exists. It's a claim about the underlying mathematical structure of physical law, suggesting that the universe might be describable at its most fundamental level, with fewer dimensions than it appears to have from the inside. This remains speculative and considerably harder to test than most of what we've discussed tonight, but it emerged from serious attempts to reconcile two of our most successful physical theories, general relativity and quantum mechanics, which don't currently fit together cleanly. Physicists don't propose ideas this strange lightly. They emerge because our best current mathematics, applied carefully and rigorously, sometimes leads to conclusions that sound closer to philosophy than physics, yet remain grounded in genuine calculation rather than speculation for its own sake. It's worth remembering, amid all of this, how relatively recent our understanding of the universe's true scale actually is. A little less than a century ago, most astronomers believed the Milky Way, our home galaxy, constituted the entire universe. It was only in the 1920s, through the careful work of astronomer Edwin Hubble, observing what were then called spiral nebulae through a large telescope in California, that we confirmed these objects were, in fact, separate galaxies entirely, vast collections of stars existing far beyond the boundaries of our own galaxy. Before that observation, the universe, as far as anyone knew, was a single galaxy, a few 100,000 light-years across. We now know it contains, within just the portion we can observe, hundreds of billions of separate galaxies, each one comparable in scale to the entire universe as understood barely a century ago. This pace of revision is worth holding onto gently. Every generation of astronomers has discovered that the universe is larger, stranger, and less thoroughly understood than the generation before them assumed. There's no particular reason to think this pattern has stopped, or that our current understanding, as sophisticated as it is, represents anything close to a final picture. The observable universe, 46 billion light-years in every direction, filled with dark matter and dark energy we still don't fully understand, possibly bounded by more universes we'll never detect, or encoded, in some deep mathematical sense, on a distant surface we can't directly observe, is simply where our current knowledge happens to stop. Not because the universe stops there, but because that's as far as our current tools and mathematics have managed to reach. We've been discussing possibilities that are, admittedly, difficult to hold in mind for very long without a slight sense of vertigo. It's worth returning for a moment to something steadier, regardless of what ultimately lies beyond the boundary of the observable universe, whether more galaxies exactly like our own, entirely separate bubble universes with different physical laws, or a universe that loops back on itself in ways too subtle for us to currently detect. None of it changes anything about the world you're resting in right now. The light reaching your eyes tonight, if you happen to look up, traveled across genuinely staggering distances and genuinely staggering amounts of time to arrive here. Some of it left its source before Earth itself had fully formed. Some left more recently, within your own lifetime. All of it, regardless of how far it traveled, ended its multi-billion-year journey by landing, briefly and quietly, on the retina of a creature capable of wondering where it came from, and what might lie beyond the point where our instruments simply run out of light to detect. That capacity for wonder is not a small thing, even set against distances this large. Every question we've discussed tonight, the size of the observable universe, the possibility of separate bubble universes, the strange behavior of an accelerating cosmic expansion, the open question of the universe's overall shape, exists because creatures on a relatively small, unremarkable planet developed the tools and the patience to ask them, and the mathematics to take the answers seriously, even when those answers point toward things we may never be able to fully confirm. There is no need to resolve any of this tonight. Physicists themselves haven't resolved it, and many of these questions may remain genuinely unresolved for a very long time, possibly permanently, given the physical limitations involved. What we are left with instead is simply the shape of the question itself, the honest acknowledgement that our observable universe, vast as it is, containing more galaxies than anyone can meaningfully picture, is very likely still just a small, local patch of something considerably larger, extending outward past the point where any telescope, however advanced, will ever be able to follow. Somewhere beyond that boundary, more of the universe continues, whether familiar or strange, knowable or permanently beyond our reach. It continues regardless of whether we ever confirm what it contains. It was there before telescopes existed to wonder about it, and it will remain there regardless of what future instruments eventually manage to detect or fail to detect about its true extent and nature. That's a reasonable place to leave it for tonight. Not a resolved question, but an honestly stated one, sitting quietly at the edge of what current physics allows us to say with any real confidence, 46 billion light years away in every direction, and quite possibly considerably further than that, in ways we may never have the tools to properly measure.